Um, my name is Siddhartha Das. I'm an associate professor in the Department of Mechanical Engineering, University of Maryland at College Park. A key aspect of my research and the research of my research group uh, revolves around understanding the fundamentals of soft materials and how they could be used for a host of applications, ranging from better understanding of 3D printing processes to uh, understanding certain very fundamental issues associated with nanoparticle lipid interaction, DNA behavior, and so on. Today, I will talk on some of my group's recent progress on modeling all are modeling polyelectrolyte brush molecules in all atomistic details. So when we talk about polymers, first thing that comes to your mind is a long chain molecule that's there everywhere. You talk about your paint, you name it, your nail polish, everywhere there is polymer. Your plastic, your everyday plastic that you have, that is creating so much problems everywhere. So there is polymers. Now, these polymers occupy a special kind of structure, like the brushes, like the bristles of the brushes, when they are densely grafted to a substrate, and hence they want to avoid each other, and hence the only way they could go is to stretch away from the grafting surface, and hence they occupy this kind of brush-like structure. So as you can see, there are examples of uncharged polymer brushes or charged polyelectrolyte brushes or charged polymer brushes, where the charge itself can be a function of pH or pH responsive polyelectrolyte brushes, or not a function of pH. Now, why somebody would be interested to understand the behavior of polyelectrolyte brush molecules? So polyelectrolyte brush molecules are ubiquitous in its presence. For example, you talk of any nanoparticle driven application, be it nanoparticle for targeted drug delivery, oil recovery, you name it. Those nanoparticles, interestingly, cannot be present in isolation. They have to be present as nanoparticles that are grafted with this kind of long molecules. The polyelectrolyte molecules are often called as ligands, so as to ensure that two nanoparticles do not aggregate, because they have large van der Waals attraction between them. To prevent that happening, they must have this kind of polyelectrolyte corona, they call it, polyelectrolyte corona around it. Very interestingly, we could also harness the responsiveness of these polyelectrolyte molecules grafted on these nanoparticles for a host of applications. For example, imagine I want a specific nanoparticle as a targeted drug delivery vehicle for a tumor. For that, it is if we could design those nanoparticles as nanoparticles that have this kind of a polymeric corona that responds to that particular tumor microenvironment, let's say the pH of the tumor microenvironment, that would be perfect. You can ensure a very specific targeted drug delivery by harnessing, by leveraging that kind of a environmental stimulus responsiveness of this polyelectrolyte molecules, affected with the pH responsiveness of that polyelectrolyte molecule. Similarly, there are applications in oil recovery. There are applications in taking this kind of polymer molecules and grafting them on the inner walls of a nanopore, on the inner walls of a nanopore, ensuring that this nanopore could open or close. That is, the polymer molecules could open, could stretch out or relax based on the pH or the ionic condition inside the nanopore. Advantage: so you can now control the transport of other ions, other biological species in this nanopore by making those polymer molecules respond. So in a nutshell, you could see that fundamentally there are great advantages in better understanding the structure of this polyelectrolyte molecules which are in brush-like configuration. And not only that, to understand the charges, the behavior of the charges, the behavior of the water molecules that surround this charged polyelectrolyte molecules. So this would be the endeavor of this talk, that we will talk about two problems. First, we will talk about how our all-atom molecular dynamics reveal, possibly for the first time, the detailed microstructure of this polyelectrolyte brushes. That is, we do not only talk about how the polyelectrolytes would behave, their structure, their height, but we also talk about the specificities of this kind of ion environment or the aqueous environment around this polyelectrolyte molecules. So we first start with the microstructure of densely grafted polyelectrolyte molecules, and let's see what this all-atom molecular dynamics reveal. So, as a motivation of this kind of an all-atom model, it's interesting to see that we can think of what has been done. People have talked about the macrostructure. They have done experiments, they have done coarse grain simulations, and have talked about the macrostructure. For example, the brush height, the monomer distribution, even the electric double layer potential, that is the electrostatic potential that this charged polyelectrolyte brush generate around it, and so on. What has been much less studied are the solvation structure of the counterions. Who are counterions? Counterions are those charge neutralizing ions that are present in the close vicinity of the polyelectrolyte molecule. The polyelectrolyte molecule that you have is charged. As you know, a charged structure cannot remain in isolation in any environment. It is quickly now neutralized by this kind of charged ions that ensure that overall there's a charge neutrality between the charged polymer and the surrounding counterions. So how this counterion structure shape up? What is the solvation structure? Who makes the solvation structure? The water molecules. So what are the arrangement of the water molecules? What is happening with hydrogen bonding? What is happening to, for example, the dielectric constant? What is happening to their mobility? That is the mobility of the water molecules and the counterions in the vicinity of the polyelectrolyte brushes. These are the questions that, to reveal which, we must invoke this all-atom molecular dynamic simulations. And this is what we refer to it as their microstructure. So very quickly, the molecular dynamic simulation details. We use all-atom model, which is an OPLS, all-atom force field, using OPLS, all-atom force field, for polyacrylic acid brushes. So polyacrylic brushes are unique in a sense that they have a COOH, that group, throughout its backbone. So when it ionizes, it has a CO minus, like along its entire backbone. That means each repeating unit, each monomeric unit would have a 1 CO minus. We have sodium ions, sodium counterions as our counterions screening the charges of the polyelectrolyte brushes, and we have SPC water, explicitly modeled SPC water. Additionally, we add salt, 0.1 molar sodium chloride salt in the system. We consider a grafting density of 3 different grafting density values. We use 3 different carbon atoms, that is different length of the polyelectrolyte molecule. We perform equilibration in NVT ensemble using Langevin thermostat. We are not going to go into the more details of this, the details of the procedure. Now, what are the first important results? So we are after the microstructure of the brushes. But to go to that point, we have to first understand, first ensure that the known macrostructure, for example, the brush height, that have been reported in other studies are indeed reproduced, at least from a point of view of scaling calculations, by our model. We do that, and we find that the brush height, as you can see, follows nonlinear osmotic brush regime. So what is an osmotic brush regime for those who are starting here? Typically, a polyelectrolyte brush molecule is balanced by 4 effects. What are they? The elastic energy of the brushes, the fact that they could stretch. The extruded volume interaction, the fact that both their intersegments, like one segment cannot occupy the other segment at the same time, nor they could occupy the location of their adjacent brush molecules. 3, the the electrostatic effects of this brush molecule given they are charged. And 4 are the electrostatic energy associated with the formation of the electric double layer or the counter-ion screening cloud that is formed around the brush molecule. Now, osmotic regime is the regime where the elastic energy of the brushes balances the osmotic pressure of the EDL ions. We also study the monomer distribution, and we find that the monomer distribution obeys a step-like profile. What does it mean? That monomer is nearly constant inside the brush layer, but the moment you go out of the brush layer, it has a quite naturally a very drastic decrease. So it's a step-like, like kind of a 1 and 0 kind of a profile, which by the way have been reported by other study, for example, by Zachka et al. in 2000. So these two kind of makes us happy that what we are doing has some kind of relevance, or our model is indeed validatable. Now we go on to the counter-ion distribution and structure. So in terms of the counter-ion distribution and structure, very interestingly, we note that those counter-ions that you have around the polyelectrolyte molecule, those screening counter-ions, they form what is known as water in salt structure. I will give a very brief background of water in salt structure. So water in salt structure idea comes from the concept of batteries, to be more specific, lithium-ion batteries. So in lithium-ion batteries, very often the electrolyte used has a very heavy anion. Let's say LiTFSI is a salt. So TFSI anion is the anion. Now, the holy grail of any lithium-ion battery or any battery, as a matter of fact, is to ensure that we can have a water-free localization of the anion at the anode. We want to carry that big anion here to the anode so that it can reduce and we can have the power generated. The problem is we cannot do that without sending some of the water molecules there. So what researchers came up with the fact that we could, if you consider a scenario where we are pumped in so much electrolyte that the electrolyte now is larger than the water in both mass and volume. So imagine a salt solution where salt is more than water in mass and volume. That kind of scenario is known as water in salt. So they found that if they did that, then because of the lack of water in the system, when you apply electric field, it is this kind of TFSI anions coordinated around the lithium ion. They move towards the anode. In other words, there are so much salt that the hydration shell or the solvation shell of the lithium ion now has some of its water molecules replaced by this TFSI anion. And that leads to very, very, very high performance of these batteries. We see something very, very similar here as well. There's nothing to do with lithium-ion battery, but this principle of some of these water molecules from the solvation shell of a small cation getting replaced by a large anion is also what we find here. I will give a more categoric explanation. Imagine this brown ion. This brown ion is your lithium, is your sodium ion, which is screening the polyelectrolyte brush charges. Now, this polyelectrolyte brush molecules are so densely grafted that now when you have so many amount of COO minus, that now you can have a coordination between COO minus and sodium plus. In other words, some of the solvation molecules of the sodium molecules get replaced by those CO minus functional groups coming out from the polyelectrolyte brush backbone. And hence, you see, we get a structure as shown on the left. That see that some of the water molecules whose oxygens are shown in gray are replaced by this pink CO minus groups. That is something is very similar to what is happening in water in salt environment. In water in salt too, because of the large density, large concentration of the salt, the lithium ion, for example, is having some of its water from the solvation shell getting replaced by the TFSI ion. Here, the sodium ion, the screening sodium counter ions, is having some of its solvation water molecule getting replaced by the TFSI ions. And we report that scenario quantitatively in this plot, where you see that as you increase the grafting density or you increase the counter ion concentration, because larger the grafting density means more number of CO minus in a given volume, hence you would need more number of counter ions in a given volume for screening. So the counter ion concentration also increases. There you find that the sodium ion solvation number that remains constant. However, the oxygen water molecule that goes down, the blue curve, the oxygen of the water molecule, that means water molecules themselves, they go down, whereas the red curve, that is the carboxylate part, that is going up. That means the replacement is occurring. Okay. Now, why water in salt? Because very interestingly, we find that around counter ion concentration of 10 molars or even less molars and less, you actually find that this hypothetical salt, which is Na plus and RCO minus, R is the rest of the monomer, that part, the both in volume and in mass supersedes that of water in that particular vicinity. So indeed, this is something very much similar to the water in salt scenario. We can actually see more statistical proof of such kind of water replacement. For example, when we study the sodium ion oxygen water radial density functional distribution, you see that you compare the blue and the red. The blue is the one inside the brush layer. That means you see the peak has come down. That means there is less number of oxygen or water molecules around the sodium ion, when the sodium ion is in the close vicinity of the polymer molecule or the polyelectrolyte molecule. On the other hand, in the bulk, where there is no polyelectrolyte molecule, these sodium ions would have a much larger number of water molecules surrounding it. This is precisely what is identified in this radial distribution function curve. Similarly, we can do the oxygen water radial distribution function. We find that its radial distribution function shifts towards the right. That is, it shifts towards the right. That is, it becomes more diffuse. Why? Because now there are less number of water molecules. So in the first solvation shell, is completed, but in a much more diffuse manner and not as compacted as it would be if it was in the bulk, where there is only water molecules. Similarly, there is a much higher distortion of the structure of the water molecules. As could be seen here inside the brush layer. Finally, the density of water molecules, the density of the water molecules, that too goes down as you increase the grafting density, that density within the brush layer. Obviously, because now over a given volume, there's a much less amount of water, much more amount of CO minus. Okay. Next, we come to the dielectric properties of water. So as you increase the grafting density, we find that the dielectric constant of water goes down. Why? Because now as you have an increase in the grafting density, that would mean an increase in counter-ion concentration. So that means as you increase the counter-ion concentration, more number of water molecules would be bound to the counter-ions on an average. So over, if you compare the total number of bound versus total number of free water molecules, the total number of bound water molecules will be more, leading to a reduction in the dielectric constant of water, because the dielectric constant of the water often depends upon the number of non-bound or mobile water molecules. Okay. Finally, we come to the mobility of both the counter ions and the water molecules inside the brush layer. You can see there's a drastic reduction. For the counter ions, we can understand because those counter ions are getting bound to the water molecules, bound to the polyelectrolyte brush molecules. Similarly, the water molecules are either now forming solvation shell around a larger number of counter ion molecules counter ions, or they are forming dipole-dipole attraction between or there's dipole-dipole attraction between the water and the polyelectrolyte brush molecule. So these are the research summary of the first part of my talk, where we have investigated in great details the structure, the microscopic structure of the water and ions for as fundamental a system as polyelectrolyte brushes. And we have identified this, for example, the radical alteration of the structure in the counter-ion solvation, water and salt-like scenario, or even a drastic reduction in the mobility. Okay. With this, we now come to the next part of my talk, where we will try to understand how this polyelectrolyte brush molecule, understanding this polyelectrolyte brush molecule in its microscopic details, enables us to pinpoint a very new kind of fluid flow phenomenon. So we will study the electroosmotic flow in polyelectrolyte brush functionalized nanochannels. So a quick description of what is an electroosmotic flow for the beginners. So electroosmotic flow is typically a flow that is people study in micro nano systems, where you have, let's say, a charged wall. That charged wall would give rise to something called the electric double layer, or an ion distribution that balances that charge of the wall. Now, within that electric double layer, there's an imbalance of plus and minus ions. So when you apply an electric field, there is an imbalance in the net ion motion. For example, if you have a negatively charged wall, there is more number of plus ions in that double layer. So if you apply electric field from left to right, the plus ions would move from left to right, more number of plus ions. So more effective motion of the water molecules, which are now coordinated, maybe through hydrogen bonding with these ions. So more number of water molecules move from left to right. Hence, there is a flow in the left to right. So typically we get counter-ion dominated electroosmotic flow. Why counter-ion dominated? For this example that I gave, the counter-ions are positively charged molecules, since the wall which induces the electric double layer is negatively charged, and it is the motion of these positive ions, the counter-ions, that dictate the overall motion. Similarly, a very similar scenario sets in, where instead of the charge on the wall, you have charge on this kind of polyelectrolyte molecules, and these polyelectrolyte molecules are grafted on the wall. So there too, those charged polyelectrolyte molecules serve as the charge center, analogous to the charges on the bare wall, and they trigger the electric double layer, and that leads to similar kind of electroosmotic flow. Of course, the presence of the polyelectrolyte molecule leads to some augmented drag force, but eventually there is this kind of electroosmotic flow. We now employ this all-atom molecular dynamics strategy to study the electroosmotic flow in charged polyelectrolyte brush grafted nanochannels. Very similar setup as done previously, like sodium ions as my screening counter ions and added sodium chloride salt. I'm not going to the details of the simulations. The first very startling result we find that the electroosmotic flow that we find first for the low to medium in the context of molecular dynamics, electric field, the flow is not from right to left as one would anticipate, rather not from left to right as one would anticipate for the case of negatively charged walls or negatively charged polyelectrolyte brushes. They are from right to left. That means they are dominated by the motion of the coions. However, as you increase the electric field, the flow field reverses in direction and becomes left to right. So two things we observe here, very, very significant in context of general electroosmotic transport. First, we find that the electroosmotic flow is coion dominated, not counter ion dominated for low to intermediate electric field strength. Second, we find that by increasing the electric field strength, there is a reversal in the direction of the electroosmotic flow. The question is why? Why this highly non-intuitive phenomenon? For that, we study first the ion distribution inside and outside the polyelectrolyte brush layer at different electric field strength. And what we find? We find for low to intermediate electric field strength, there is a phenomenon of overscreening inside the polyelectrolyte brush layer. So what is overscreening? Imagine the polyelectrolyte brush are negatively charged. Let's say, just for a sake of number, let's say the total charge is, let's say, 100 electronic charge. Overscreening means we have not only made the net charge neutral, that would be the case, expected case with all the counter ions coming in, positively charged counter ions coming in. We have made the overall charge of the brush layer positive. So let's say it has become, let's say, plus 10 instead of minus 100. It would be 0 ideally with all the counter ions, but now I have made it plus 10. That means I have more number of counter ions than needed to screen its total charge. This scenario is known as overscreening, and we find this distinct overscreening as can be seen from the leftmost image for our setting. And as a result of overscreening, we find that there will be now less number of positive ions in the bulk as compared to the negative ions. The less number of counter ions than coions coming from the added salt. So that can be seen from the central picture. See the case of electric field of 0.1 volts per nanometer. You see the red one, the zoomed in one. That's the case happening outside the brush layer. That is very important because that is what is happening outside the brush layer that will dictate the flow. There you see that there are more number of coions as compared to counter ions. However, as you increase the electric field strength, see what is happening at the rightmost picture. This difference is going down. The overscreening is no longer there. So now, why this overscreening? Let's look into this phenomena very quickly, and that would help us understand. So firstly, the overscreening is caused because of large confinement effect, because we have a nano channel. If we had done a single channel, like a single surface, no confinement, you won't have an overscreening as given by this image. Why this is happening? For a large confinement, the ions experience large osmotic pressure in the bulk, so they want to move away from the bulk into the brush layer. Next is the ion specific effect. So this large osmotic pressure is true for all ions, sodium ions, chlorine ions. If you use another, for example, we did simulation with cesium fluoride salt, cesium ions, fluoride ions everywhere. Why sodium only goes in? Sodium only goes in because of two things. One, sodium has a much small size, so it can go in. Second, equally importantly, sodium has a very large charge density. That would ensure that you can form a very stable CO minus Na plus entity that stabilizes the sodium ion inside the polyelectrolyte brushes. So sodium ions can overcome electrostatic repulsion by virtue of the fact that they are attaining extreme stability as they form coordination with CO minus. And this is actually studied, this is actually confirmed by the free energy calculation, where we find, as you can see, there are two minima in this sodium ion distribution plot. So what we do, we consider a brush layer and a charge, an overscreen brush layer, take a sodium ion, consider a different location and study the free energy. You see there are two minima. That means energy stabilized over there. Sodium ion prefers to be there. So finally, we also established that this overstraining is a generic mechanism, and it is true for other grafting densities, other salt concentration, other types of polyelectrolyte molecules. Like we had done polyacrylic acid, all the results, these are the results for PMMA brushes. There too, we see the overstraining. So to summarize, there's overstraining because of a combination of nano confinement and ion specific effects. Nano confinement leads to high osmotic pressure, but the ion specific effect leads to small ion size and the high charge density that leads to this very interesting phenomena of overstraining. Now, this overstraining means there is excess of coions in the bulk for low to intermediate electric field. Hence, the electroosmotic flow occurs in the direction of the motion of coions. Now, what happens at larger electric field? You see, I will be quick here for the sake of time. As you increase the electric field, the brush height decreases. The brush height decreases. And as the brush height decreases, this happens because of the tendency of the electric field to cause a preferential orientation of the polyelectrolyte functional group counter ion pairs. So as the brush height reduces, the counter ions squeeze out those excess counter ions that's caused overstraining. They squeeze out, so overstraining goes away. That means you now have, as you saw previously, there is no difference in the number of coions and counter ions in the bulk. What is then causing the electroosmotic flow in the direction of counter ions for large electric fields? We study the ionic velocities. At large electric fields, the picture on the right, there's not much difference between sodium and chloride ions at large electric fields. Then what's going on? We now study the residence time. This is the last important thing we are talking about. We talk about the residence time. That is, we study how long the water molecules reside in the solvation shell of these ions. And we find that for both large and small electric fields, the time for which the water molecules reside in the solvation shell is much larger for the case of sodium ions as compared to the chloride ions. That means the sodium ion motion will better coordinate the motion of the water molecules. And this is the reason why at large electric field, where there is no other effect, no difference in the bulk number of coions and counter ions, no difference in the ionic velocities, it is this effect, this large difference in the residence time, that will drive the electroosmotic transport at large electric field in the direction of the motion of the counter ions. So very quick summary of the flow results. Low to intermediate electric fields, higher coion concentration in bulk plus higher coion velocity, coion dictated electroosmotic flow. High electric field, higher residence time of solvation water for counter ions, hence counter ion dictated electroosmotic flow. And this ensures flow reversal at some critical electric field strength. We also studied the case of a more experimentally realizable setting where there is a nano channel supported with bulk micro channel reservoirs, and we find the same kind of overstraining happening. Overstraining means we will have same kind of flow reversal and coion dominated electroosmotic transport for low electric field strengths. For low to intermediate electric field strength. So to very summarize this second part of the work, we have discovered monovalent counter ion mediated overstraining in polyelectrolyte brushed functional nanochannels. This overstraining coupled with large ionic coion mobilities triggers coion mediated electroosmotic flow for low to intermediate electric field strength. And finally, at larger electric fields, there is no overstraining, and the electroosmotic flow occurring in the direction of the motion of the counter ions is caused by the greater residence time of water inside the counter ion solvation shell. Finally, I would like to acknowledge the people and the funding and the support behind this work. I would like to gratefully acknowledge the contribution of my co-PI, Dr. Peter W. Chung, of my mechanical engineering department as mine. Also, the work of the students. The first work the first work on the microstructure of the polyolid brushes was by Dr. Harnoor Singh Sachar, who is currently a postdoc at UT Austin. The electroosmotic flow work was primarily by Mr. Tura Shakpiyal, who is a PhD student. Also contributed to this work are other PhD students, Mr. Path Raket Desai and Sayanki Tetha, and also my former PhD and postdoc, Dr. Yanbin Wang, who is currently a postdoc at Purdue University. I would finally like to gratefully acknowledge US Department of Energy, Office of Science Research Grant, who for supporting this research, and Deep Thought Tube, high computing resources at University of Maryland, which we use to perform the simulations. Thank you very much for your kind attentions, and I would be happy to take any questions.